This is a Wiimote, a remote control for the Wii video system, and it has an infrared camera in here. And it can wirelessly report the location of infrared points that it sees to the computer. Johnny Chung Lee showed that we could use this as a simple light pen. The first thing you have to do to use it is find the mapping from the points in the camera's coordinate system to the points in the screen coordinate system. Now, how do we find that transformation? The transformation can be represented, as we'll see, by a matrix H. And the challenge is figuring out the matrix H. We can derive H, essentially, once we take 4 points whose coordinates in the screen coordinate system are known and find their representation in the camera coordinate system. We're going to use the same math for a slightly different problem, removing perspective. Here's an image taken in my office of a whiteboard, taken from an angle. Now, there might be some interesting linear algebra written on this board, but we can't quite get it because it's taken from an angle. So what we'd like to do is synthesize a new image from this image, looking straight at the board and with no perspective at all. And here's the result. Now, how do we do that? We use the same camera-oriented basis as before. Remember that the origin is at the camera center. The first vector in the basis goes horizontally. The second goes vertically. And the third goes from the camera center, from the origin, to the top left corner of the image sensor array. We're going to make use of another coordinate system, one that's particularly well suited to the whiteboard. Okay? In this coordinate system, the origin is, as before, the camera center. The first vector in this whiteboard basis goes horizontally from the top left corner to the top right corner. The second vector goes from the top left corner vertically down to the bottom left corner. And the third vector in the basis goes from the origin, the camera center, to the top left corner of the whiteboard. So you have to imagine these vectors in the three-dimensional world. Now, let's say we have a point in the world, and we have its coordinates in terms of the camera-oriented basis, A1, A2, A3. We can write the same point P in terms of the whiteboard coordinate system, C1, C2, C3. Here are the coordinates in terms of the camera basis. Here are the coordinates in terms of the whiteboard basis. Now, combining these two equations, we get this equals this because, of course, it's the same point. So we've got this equation. And now I'm going to basically be recapitulating an argument I made earlier having to do with change of basis. Let A and C be these two matrices. And as before, when we were discussing change of basis, this matrix C has an inverse, C inverse. Let's multiply this equation on the left by C inverse, and we get this equation. Now, C inverse and C cancel out, giving the identity matrix, which multiplied by this vector doesn't change it. So we get this equation. So the product of the matrix C inverse and A is a matrix H, such that H times the coordinate representation with respect to A1, A2, A3 equals the coordinate representation with respect to C1, C2, and C3. The challenge is computing H. We don't actually compute this matrix H by multiplying two matrices. We compute it by solving equations. We think about the entries of the matrix H as unknowns. We set up some equations in these unknowns, and we'll use the solver module to solve this. The math is a little hard to follow. It'll make more sense once you start actually doing this. So to derive the equations, let P be some point on the whiteboard, and let Q be the corresponding point in the image plane. Let x1, x2, and 1 be the camera coordinates of the point Q in the image plane. that is the coordinates with respect to the camera basis, and let y1, y2, y3 be the whiteboard coordinates of the same point Q. So then we have that the vector y1, y2, y3 is the matrix H times x1, x2, and 1. Now let's multiply everything out, and we get these equations. So here are the equations. The whiteboard coordinates of the original point, P, are y1 divided by y3, y2 divided by y3, and y3 divided by y3, which is 1. So let's define w1 to be y1 over y3 and w2 to be y2 over y3. So we can write the whiteboard coordinates of this original point P as w1, w2, and 1. Now let's multiply through these equations by y3. So we get these equations. Now we use these to substitute for y1 and y2 and y3 in these equations, and we get these equations. Now finally, multiplying through and moving things to the other side, we get these fairly complicated equations. The equations are equations in the unknown h entries, and the coefficients in these equations are known values. They're coordinates of points we know about. So we got two equations in these unknowns from looking at a point in the whiteboard and the corresponding point in the image plane. Now that gives us two equations. We're going to take 4 points in the whiteboard, namely the 4 corners of the whiteboard, and find out, using an image viewer, the coordinates of those points in the image plane. We find out which pixels they correspond to. We can use that in this way to derive 8 equations in the unknown entries of the matrix H. Unfortunately, there are 9 entries in the matrix H. So that doesn't quite give us enough information. We need one more equation. But it turns out we can't figure out what H is from these points after all. This corresponds to the fact that we don't know the scale of the image. Okay? A tiny building that's nearby looks just like a huge building that's far away. But it turns out that doesn't matter. The scale of the image doesn't matter when we're doing this transformation. So we don't have to pin down exactly H. As long as the H we compute is a scalar multiple of the true matrix H, we'll be able to perform the transformation just fine. So in order to pin down some H, we just add an equation. We specify that one of the entries is 1, and that should work out okay. Again, the math is fairly confusing. Once you start actually performing these calculations, I'm hoping it'll become more clear to you. All right, let's say we've computed the matrix H. How can we use this to synthesize an image without perspective, an image of the whiteboard without perspective? We have an image. It's a grid of pixels. Each pixel is a rectangle of color. What we have to do is transform that rectangle to find out the corresponding quadrilateral in the whiteboard. So we know the coordinates of the little rectangle in the image plane. It's given by the camera coordinates. What we want to do is find out the corresponding points in the whiteboard coordinate system. So we start with a point Q in the representation of the image, and we have its camera coordinates. We know what pixels it corresponds to. Take each point, each corner of a pixel, multiply it by h to get the representation of the same point with respect to the whiteboard coordinates. Now, given the representation with respect to the whiteboard coordinates, it's easy to find the corresponding point on the whiteboard. So here's a point in the image plane. We want to map it to this corresponding point in the whiteboard. And we know that the way to do that is to just scale down, divide these coordinates by the third coordinate. and that gives us the point in the whiteboard. So you write a program to carry that out for each corner of each rectangle of color in the image. Transform those, and you'll get a new image that's of the whiteboard with no perspective, looking straight on. This will be more clear when you start doing the lab, and it's spelled out in greater detail in the lab assignment.